All right, so Unit 6 was all about functions. So first of all, we need to talk about what a function is. It's a relation in which every element of the domain is paired with one and only one element of the range, aka we always say that every x has only one y value, and the graph needs to pass the vertical line test, which means that if you have some function like that, if you draw a vertical line, it only hits it once. That's passing the vertical line test. Keep in mind in this unit that domain is all reals. Oops, excuse me. Domain can be described as all reals. The domain is your x's and the range is your y's. So determine if each of the following are functions. State the domain and range and any transformations on the function if possible. So based on what you guys would have just reviewed with Unit 4, you should know all about parabolas. I see a y equals parabola with a leading coefficient that's positive, so that means it's going to open positively in the y direction. So that does pass the vertical line test, so yes, that is a function. Transformationally, I know that this is a vertical compression of 1/4, and this means left 6, down 3, which is why this vertex would be at -6, 3. The domain of this would be all reals, and the range, because it's opening upward, would be from 3 to infinity. If I look at a set of points, so this set of points in terms of letters A, B, and C, I'm noticing that B is happening twice. I can't have the x's repeat. Remember, every x has to have only one y value, and right now it has 2, so this is not a function. Okay. Next two I'm not going to do. You guys can just plug in your calculator and look, but each of these would be functions. They would be on the, they would pass the vertical line test, and you would be able to find the domain and range of them from the graph. Moving on to piecewise functions. They are literally just pieces of functions together. When you come up with equations of them, you read them like a story from left to right. So the first thing I'm noticing, obviously with this arrow, is that that makes up this function right here, which is your y equals x squared parabola. Then it looks like I jump down here at a point, 2, 1, and then I finish with a horizontal line at 4. So putting it all together, it's x squared, and then y equals 1, and then y equals 4. And I just have to state on what interval this is happening. So I always ask myself, for how long am I going to be y equals x squared? So from negative infinity to 2, so I'm looking at the x-axis, is when I'm going to be the parabola, but not including 2. So that means I'm going to be on the domain x is less than 2. Notice I used the less than symbol, not less than or equal to, because of this hole in the graph. Then it goes down to 1, or to 1 I should say, at x equals 2, and that is filled in, so that's an equal sign. And then we're open again at y equals 4, so this is going to happen as x is greater than 2. Okay. If I asked you what f of 2 is, that would be where the solid dot is. So f of 2 is 1. Average rate of change is calculated by doing our slope formula. So remember, slope is y2 minus y1 over x2 minus x1. Please do not forget that. If you switch the x's and y's, historically you've lost 50% of credit on questions, so please make sure you don't mess that up. Sometimes we think about it instead as like rise over run, or we also have done stuff like, excuse me, delta y over delta x, so change in y over change in x. So given the functions g of x, f of x, h of x shown below, which has the greatest average rate of change on the interval, and justify your answer. Please pay attention to the interval. That's what students tend to forget to do. The easiest one to start with is the table. I literally will circle in the table where x equals 1 and x equals 3 is. And then I just apply my slope formula. So 54 minus 6 over 3 minus 1. And that gives me 48 over 2, which is 24. On the graph, pick out your points. I've got 1 and 3.25 and 3, 9. So change in y, or change in x. And that goes to 2.875. And then lastly with this, you could either evaluate the function at the values 1 and 3, which I'll do that actually first. Okay, so that gives me 9, and then g of 3 gives me 19. 19 minus 9 over 3 minus 1 gives me 10 over 2, which is 5. And when you think about that, that actually makes sense because g of x is a line, and the slope of that line is 5. Okay, if you didn't notice that right away. Another thing you could do is pull up your graphing calculator. Whoa, mine's huge. 1 second. There we go, that's better. You could always just take whatever function that they give you. This is pretty straightforward with a line, but like let's say it was a quadratic or a cubic or whatever. You could just plug it into y equals and look at your table of values and then calculate your average rate of change from there. Again, you're only looking on the interval of 1 to 3. Alright, on to operations of functions. They are exactly what they look like they would be. Addition, multiplication, subtraction, and division. And just like that, they're all magically filled in. Okay, great. So when functions are added, subtracted, or multiplied, the domain doesn't change. The domain will have to be recalculated, though, if we are to divide functions. And that has to do with the whole, we don't want any denominator to go to 0 because then the function would be undefined. So before we get into actually performing those operations, let's just talk about the domain for these graphs that I'm going to be dealing with. So first of all, f of x is a line with a slope of 3 and a y-intercept of -5. So it would look like this, roughly. So that means the domain is all reals. This is a square root function with a vertical stretch of 2 that's been shifted to the left 1 unit. So it looks like that. And you could always verify these with your calculator. So that means the domain is from -1 to infinity. And then, write this parenthesis. There we go. And then lastly, this is a parabola. Specifically, I don't know the vertex because I can't factor that, but I know it's a happy parabola. So it looks like that. And that means that the domain is all reals. Okay, so performing operations. If I am doing g plus f of 10, that means evaluate each of those functions separately at 10 and then add them together. Okay, so this is g of 10 plus f of 10. So g is over here. F is right here with my line. Okay, so that doesn't simplify too crazy much, but it is what it is. So this is 2 radical 11, and that's 30 minus 5, so plus 25. Okay, can't combine that any further because you can't combine that if it doesn't have a radical 11 on it. Okay, on to the next. I'm not going to do this all the way out, but you would just evaluate the k function, which is this parabola at -6. Evaluate the f function at -6 as well, and then you just multiply those together. So just to save us some time here, that would be 71 times -23, which is -1633. Okay. Now let's get into subtraction, where I'm not actually evaluating it at a value, but rather over all of the x's. This says take my f function, which is 3x minus 5, and subtract my g function, which is 2 radical x plus 1. Okay, I actually can't combine that any further. It's not very exciting. But what I am going to do here is talk about the domain of it. Now, 3x minus 5 itself has a domain of all reals. But this part of the graph, or g of x I should say, had a domain restriction. It was on the domain of -1 to infinity. So that means once I combine these two functions together, it's just going to take on any restrictions that the original functions had. Okay? Now if I had combined two functions that were both all real domains, well then the domain would just be all real still. Now I come over here where I have division, and this is saying take x squared minus 6x minus 1 and divide it by 3x minus 5. Now each of those separately have domains of all reals, but as soon as I divide them, I have a rational expression, and therefore I need to really pay attention to where the denominator goes to 0. So in this case, my domain is going to be all reals, but x cannot be 5/3 because, again, that would cause that denominator to go to 0. So that's where you have to be careful. Okay, so moving on along to compositions of functions, just remember that we do these backwards, or inside to outside with the nested notation. So if I give you two functions and I want f of g of 2, you're first going to evaluate the function at 2, which goes to 1, and then now I take 1 and plug it in f. And 2 would be your final answer. Now this is not commutative, meaning if I change the order, I'm not going to still get 2. Watch what happens. So that gives me 3, and now I'm doing g of 3, which is 3 squared minus 3, which is 6. So you can see I do not get the same answer, so it is not commutative. Now, when I do this for all values of x, so not just 2, all values of x, I'm composing the two functions together. So essentially, I'm coming up with a new function that combines plugging into g first and then plugging into f. So I read this as I'm plugging g of x, which is this, into my f function. So I'm literally taking this and subbing it in for my f function, which is x plus 1. But instead of writing x, I'm going to write my g function. I'm going to write x squared minus 3x. Or x squared minus 3, excuse me. And that would be the composition of the two functions. So this would be x squared minus 2. So again, here's what this means. This function that I just came up with, x squared minus 2, is going to do the work that a did in two separate steps. Because this says plug into g first and then go into f. So if I evaluate this function, x squared minus 2, at 2, I should get 2 just like what I did over here. So let's see, if I put 2 in, that would be 2 squared, which is 4, minus 2, which is 2. Okay, so these are actually related. Okay, so again, this just means you're taking the g function, plugging it in for f. Everywhere you see an x in the f function, you would replace it with the actual expression that represents g. Alright guys, the last thing we need to talk about is inverses. So I'm going to look at the original function y equals x squared on the interval of 0 to 3. So 0, 1, 2, 3. And then I'm also going to look at its inverse. Alright, so the big idea here is that this purple graph, this is my original function, this is y, and then this pink graph would be y inverse. What we just did was switched all the x's and y's in the first table to get the second one, which is the same thing as reflecting over the line y equals x. So if I were just to sketch in what that looks like, okay, that's the line that you would be reflecting over. Okay, so we're going to take that concept of switching x and y to find algebraically inverses. So if I want the inverse of a, I just simply switch x and y. And now the name of the game is solve for y. So I'd take the cube root, subtract 4. Okay, but instead of saying y equals as my final answer, it would be y inverse equals the cube root of x minus 4. With fractions, it gets a little bit trickier. Switch x and y. Okay, now you want to get the y's together, but not in the context of division, because right now that's not going to be very helpful. So I'm going to get rid of the fraction. I'll do some distribution. And I'll just do a little bit of rearranging so that my y's are next to each other. So I subtracted the y, added over the x. Now the objective here, again, is to create one y that you're solving for. So I can factor out a y as a GCF. And now it's pretty easy to see that to solve for y, I would just divide by x minus 1. Okay, so then y inverse would equal x over x minus 1, which midway doing this problem, I just realized I got the exact same function back, which I promise you does not always happen. So I came up with another example so it's not as lame. So let's quickly do this. Yay! So if I want the inverse of this, just like the last example, I'll switch x and y, get rid of the fraction, distribute, and then get my y's together. So maybe I'll just leave the 5x over here and do y minus xy. I'll factor out the GCF of y, and then just divide by 1 minus x. So this is one where I did not get the exact same function back, so it's more exciting. So y inverse equals 5x over 1 minus x. Now, that is more exciting. You could graphically verify these two to see, does it look like it has been reflected over the line y equals x? So let's actually do that with this first one. So let me pull out my calculator. Okay, so in my graphing calculator, I just put in the original function, the inverse that I found, and I'm going to put in y equals x just to show you how it looks like it's reflected over that line. And I'll graph them. So that's our first function, that's y, and then this next one coming in is y inverse. Here comes y equals x. And you can see how if you were to fold the graph along this line, this function would map onto its inverse. Okay? And that's how you could graphically verify your work.